Hi everyone, I'm Dept, the chairperson of the Cambridge University Astronomical Society. It's good to be back here with everyone for our first in-person talk of the term. So just a general reminder that everyone should wear your mask unless you are medically exempted. Tonight, we are very honored to have Professor Nial Tanvir from the University of Leicester with us to give a talk titled Merging Neutron Stars, Kilonovae, and the Origin of Heavy Chemical Elements. Before we begin, here's a short introduction about our speaker. Professor Nial Tanvir obtained his BSc in Mathematics and Physics at the University of Durham. He stayed in Durham to do a PhD entitled Resolved Stars in External Galaxies under the supervision of Dick Fong and Tom Shanks. After the short postdoc in Durham, he moved to the Institute of Astronomy in Cambridge, where he was a member of the UK Hubble Space Telescope Support Facility. In 1999, he was appointed a lecturer at the University of Hertfordshire, and in 2006 moved to Leicester as a professor of astronomy. He has sat on many scientific advisory committees, and in 2002 was a co-president of the European Union Descartes Prize for Research, recognizing pioneering contributions to the study of gamma ray bursts afterglows. He was awarded a PPARC Senior Fellowship in 2005. He is also actively involved in public outreach, giving frequent talks to schools, societies, and public audiences, and making occasional TV and radio appearances. Now, without further ado, Professor Nial Tanvir, please.
Okay, thank you very much for the intro. Very nice to be here with a live audience and indeed a hybrid setup here. The title I now realize is obviously slightly different from what I've got on the screen, the one that I obviously suggested, but actually the topic is the same. So what we're going to talk about are these things, short duration gamma ray bursts, things called kilonovae, and things called gravitational waves. And if you are not so familiar with any of those, then hopefully by the end of the talk, you will be at least slightly more familiar with them. So a subtitle for the talk might have been, if it glitters, it may be gold. And hopefully the significance of that will become clearer as we proceed. This really challenged my PowerPoint skills, let me tell you, to make this. So onward, what is the talk actually going to be about then? So essentially we're going to talk about three very long-standing astrophysical challenges, and by that I mean problems and puzzles that have gone back many, many decades, and recent breakthroughs that have made big steps to resolving those. In the first case then, we're going to talk about a very dramatic and exotic kind of explosion, things called short duration gamma ray bursts. That's the GRBs. I'll usually call them GRBs. There's the question of where the heavy chemical elements come from, and a particular heavy chemical element might be gold that you may have in your finger as an example, but actually there's a pretty big mystery that again goes back many decades regarding the origin of many of the heavy chemical elements that we know of in the Earth and in the universe. And then finally, there's the very long-standing challenge to detect gravitational waves, which anybody that's been taking notice will realize there has been great progress on that front just in the last few years. And it turns out all these things are connected, and I'll try to weave these stories together so that hopefully you understand those connections by the end, but if not, there's plenty of sort of wow factor on the way through, very interesting stuff that we'll be talking about. So to start with, I'm going to let Einstein open the show. We're going to start by talking about gravitation, and this picture was taken at what is now the Institute of Astronomy, was then just the Cambridge Observatory in 1930, I think, and there is Einstein talking to Eddington, and he's commenting that gravity is not actually a force. Newton, of course, told us that gravity was a force that acted between any two massive bodies, but Einstein had a different perspective. He said it's not a force, it's instead a consequence of the warping of space-time. And so Eddington can educate us by saying that what that means is that falling objects are actually following straight lines through curved space-time. What might that look like? Well, of course, curved four-dimensional space-time is not an easy thing to envisage. So instead, what we can envisage is at least a two-dimensional surface that is somehow curved in a third dimension. And so it would look something like this. And we get a feeling that if you were to roll a marble around this curved surface, then of course it's going to follow different trajectories without any force pushing it one way or the other, but just because of the curvature of the surface. And so that if you were a little ant living on that surface and you could only move in two dimensions and you were only aware of two dimensions, you would see, for example, this particular ball going round and round there with apparently orbiting the central dip, but you wouldn't be aware of the fact that it was actually just following a straight line and a curved surface. So that was Einstein's explanation for gravity, and it carried a consequence, which is that if that was true, then space-time should also be something that can ripple, that information and energy can travel through ripples in space-time, something that we call gravitational waves. And Eddington was sufficiently interested by that idea that Einstein had proposed that he went on to investigate it as well in the 1920s. Let's have a look at what gravitational waves may look like then. So in order to generate gravitational waves, it turns out you need pretty big masses and you need them to be accelerating fast. And so the most obvious way you might get that is if you had two black holes in orbit around each other. As they get closer and closer together, which they will do because they're losing energy through these gravitational waves, they will, as we'll see in a moment, start to deform and eventually merge. And then this all happens very quickly. You can see the time counter there counting down. And when they do so, they'll merge to form an even bigger black hole. And then the camera angle will pull back and we'll see the gravitational waves that have been produced in a kind of schematic way, rippling away from this merger event. So that's just the point where the event horizons of the two black holes coalesce, and then the black hole very rapidly becomes spherical again. And if we pull back, we should now see, at least in this schematic way, those ripples going off through space-time. So it's that we would like to detect. In order to detect such things, it turns out you need very long arms. So arms in question are examples like this one here in Washington State in the US that are 4 kilometers long, and they're arms that are tunnels that are evacuated where you can shine a very powerful laser down both arms, and then you can bring it back and you can interfere the light, and you can try and see whether there's any change in the lengths of those 4-kilometer arms. And so just from the point of view of understanding the physics, what we're doing is we're setting this up so that if there was no change in the arm length, then we get destructive interference and we wouldn't detect any light coming out here to the detector. But as we'll see in a moment, if the arm lengths vary, then you can get some element of constructive interference. It's not perfectly destructive at least. And so you will start to detect light out of this detector. And so this is a way of detecting whether there are slight fluctuations in these arm lengths. And those slight fluctuations, we believe, will be produced by gravitational waves coming through the universe from some distant event, passing through the Earth, passing through our apparatus, leading to these very small changes. How small, I hear you ask? Very small, okay? So we're talking about fluctuations in these 4-kilometer arms at about the sort of 1,000th of a proton size. So spectacularly ambitious kind of experiment to imagine that one could construct an interferometer to probe those tiny, tiny changes. Of course, these kinds of facilities are extremely good at detecting other kinds of vibrations, earthquakes, waves rolling into the sea, for example, into the beach nearby. All these sorts of things will have a noticeable effect on these kind of detectors. And so one has to work very hard to remove those kinds of sources of unwanted fluctuations in order to detect your gravitational waves. Anyway, the big news was about 7 years ago, 6 years ago, the first example, after about a 50-year search and build up to this point, the first example of a gravitational wave was found, and it behaved exactly as we would expect, as had been predicted, for the merger of two black holes of a mass something like 30 times the mass of the sun. And you can see here, this was a signal that was detected. There were two detectors in the US that detected the signal simultaneously. I won't bother explaining everything on this figure, but you can basically get the idea that it looked just like what had long been expected. It happened on the 14th of September 2015, which was a surprising date because officially the science run was supposed to start on the 15th of September only. And those of us that were following this game had all been expecting some news potentially from the 15th of September onwards. It turns out that during the sort of the final engineering checks before they turned the whole system on, they found this really rather bright event, as it goes, or loud, as they would normally say. And so it was a stroke of luck, really, that this event was seen. So the gravitational wave detectors, as you may know, have carried on operating intermittently over the last 6.5 years. So they have periods when they're switched on for maybe a year or so, and then periods when they're switched off and upgraded to become more sensitive. And during that time, a number of things have happened. One is that the European equivalent detector called Virgo has started operation, and indeed so has the Japanese Kagra detector, very much at the end of the last science run. And they've detected a whole lot more binary black holes, and so this picture shows you that. You won't see it very clearly on the left-hand side, but that is the mass of the systems, and in each case, basically, you've got two blue dots merging together to make a more massive black hole, and that's the sort of top blue dot, and the mass is also indicated by the size of the symbol there. And so it's really been very successful. A whole bunch of these black holes have been detected. Masses here up to, well in excess of 100 times the mass of the sun. However, so that's tremendously interesting and an enormous breakthrough. But the thing that is interesting from the point of view of our talk are the little orange points there at the bottom. So those orange points are actually not black holes, those are neutron stars. I imagine many of you know what neutron stars are, but I'll describe them later on, and they're going to come back periodically through the talk in actually a number of different ways. So neutron stars, in brief then, are one step before you form a black hole. They're the densest kinds of objects which are not black holes, and so they're incredibly dense. They can also take part in these binary in spirals that create gravitational waves. But you'll already see that clearly there are not as many of those being detected as there are the black holes. We didn't, before the detectors started to detect these mergers, have a good idea what the ratio was going to be between blue points and orange points in this figure. Many people would have expected a lot more orange points because we know there are a lot of neutron stars out there. We had much less idea of just how many black holes there might be. And so this has been one of the discoveries really of LIGO and Virgo to appreciate just how many of these binary black holes there are out there. Okay, so that's gravitational waves. We're going to park that for a little bit, come back to it later. We're now going to turn our attention to this question I raised right at the beginning, which was, where do the chemical elements come from? And so we're kind of familiar with the periodic table, and typically you learn about this sort of thing in school and you don't even ask that question, you just take it that that's what is there. You probably have an idea that some of these ones right at the bottom here, the very massive radioactive elements, turn out to require human involvement in their creation, but the others you just sort of assume are, in a sense, God-given. However, of course, if you're a scientist, you'd like to probe that a bit more. You'd like to understand whether the chemical elements that we see and the different abundances of different elements make sense, and especially make sense in the context of our ideas of how the universe came into being and how it has evolved. In other words, in terms of the Big Bang theory. And so thinking about the Big Bang theory, we can ask, what do we think the Big Bang produced in the way of chemical elements? And that turns out to be a rather limited answer. The answer is, we think that the Big Bang very substantially just produced hydrogen and helium. So the two simplest elements, hydrogen there just with one proton and electron, helium, of course, with two protons, two neutrons typically, and two electrons. And that was more or less it coming out of the Big Bang. So there really is a puzzle then here. We need to know how all of the other chemical elements, things, for example, that we're made out of, like carbon, oxygen, etc., where did all that come from? What was realized much around the same time, in fact, that Eddington and Einstein were talking about gravity, and indeed, again, particularly involving Eddington in this regard, many of those chemical elements are going to be cooked up in the centers of stars. So nuclear burning was realized to be the likely power source for stars. And if you burn hydrogen and helium in the cores of stars, then of course you're going to build up heavier chemical elements. And that could all be worked out. What it leads you to conclude is that particularly in massive stars, once they exhaust their hydrogen, they start burning helium in their cores, and then they start burning carbon and oxygen, etc. And by the end of their lifetimes, the point when they can effectively create no more energy, a massive star will have a lot of iron and nickel in the core, and then successive onion skin layers of other lighter elements working out towards essentially the sort of pristine material in the outskirts. So that is what we expect to happen in stars. And of course, we know that massive stars as well, at the end of their lives, frequently explode as supernovae, as this artist's impression shows you. And so at that point, they can spray those elements out into the cosmos. Those can get then formed into new planets and solar systems, etc., and people and what have you. So, that's where we think it comes from. And so famously, I think probably it was Carl Sagan said, we are all made of stardust. However, turns out that's only part of the story. Let's have a look at this plot here. What we have here is the mass number of different chemical species. So going from hydrogen of mass number 1, helium mass number 4, etc. This is a logarithmic plot of their universal abundances. And sure enough, hydrogen and helium, which we said were created in the Big Bang, dominate the total amount of material in the universe. But we do have plenty of other heavier elements here, particularly out to this iron peak here, which we said was the end of nuclear burning. So we've got, maybe a quarter or a third of the way up towards what we know. I mean, this doesn't even have the final elements of the periodic table here. What we know exists in the universe. And we can see that it decreases as we go to these heavier elements. Clearly, there's not a lot of these heavy metals, for example, compared to these lighter elements. This is many orders of magnitude less, but they're not negligible. They exist, okay? And so this needs to be explained. If it's not going to be star burning of nuclear fuel in stars that creates them, how are we going to create them? And can we understand their distribution, which obviously it goes down like this, but there are these interesting and suggestive looking peaks at particular points in this plot. And that was a question that was very much on the mind of scientists in the 1950s, and in particular Fred Hoyle, who was also a largely Cambridge man, although a lot of the work that I'm about to describe carried on when he was in fact working in the States. And what Hoyle and his colleagues realized was that perhaps the most effective way of building up these even heavier elements, heavier than iron, was within stars, again, to fire neutrons at the existing heavy nuclei. So you've got some heavy nucleus, maybe it is iron. Within the plasma in which these nuclei were floating around, there, at least in some circumstances, there'd also be free neutrons. And those free neutrons could be absorbed reasonably readily into these heavier nuclei because they're not charged, and so they can slip in there kind of unnoticed, rather harder to get a proton into a nucleus like that. And so if you do that, then, well, you've made your nucleus into a different isotope. You've added one neutron to it. You've still got the same number of protons. But it may be that you can add neutrons to the point that you then create an unstable, radioactively unstable nucleus. And at that point, it's likely that one of the neutrons within the nucleus is going to turn into another proton and release an electron. And that balances charge. It's called beta decay. That then means you have then created an element one up on the periodic table. Well, so rinse and repeat. You do this many, many times in certain stars, and you can slowly build up heavier elements. But it is a slow process. It was called the S process for that reason. They realized it had to be slow because actually these neutrons are actually rather few and far between. So the chances of acquiring one through this neutron capture were not great. And so if the radioactive decays are likely to be happening on faster timescales, then they will be dominating. However, this is just a picture of that process that I've just described. So, but important physics point for those of you that are interested in the physics, nuclei are hard to model, but when we do model them, we realize that if one does so and treats them as quantum mechanical systems, then you expect that the protons and neutrons to kind of fill up shells in a kind of similar way to that in which electrons fill up shells within atoms. And you conclude that there should be particular configurations, numbers specifically of protons and neutrons that make particularly stable nuclei. So that's kind of promising. Without going into the details, those are some of the numbers. It's kind of promising because remember, we saw those peaks in the distribution of the nuclei. So it could be that those peaks represent these particular magic number nuclei and therefore are favorable. And so it turns out to be partly, but that's only part of the story. Well, actually, let's go back to it. Yes, so the peaks that you can explain that way are these ones that are labeled S. So they're barium, here at lead, here at strontium. Those can be explained that way, or at least some of the isotopes of those elements can be explained that way. Harder, much harder to explain, come back. Much harder to explain were these peaks just to the left of those S peaks, things that are called R. Well, if S stands for slow, you can imagine that R probably stands for rapid. What Boyle and others realized was that if you had a situation somewhere in nature where the neutrons, instead of being plopped in to the seed nuclei every, few tens of thousands of years or something, if instead they were going in very rapidly, perhaps on timescales of seconds or less, then that way you could build up really very unstable and exotic nuclei. And the decay of those, once you turned off the neutrons, would then produce peaks that were offset from the S peaks, just as we have it. Now, to illustrate that point, that's just to remind you that that's where gold lives. I've got a little diagram here. So what's this diagram? It's going to turn into a movie in a minute, but let's just have a look at it. What we have here is neutron number plotted against proton number. And the black squares there are basically the stable nuclei that we know exist in nature. And if you wander away from those black squares into this sort of region, then you're getting radioactive nuclei, things which might be fairly long-lived, or they might be, the further away we get from this sort of zone of stability, they might be very short-lived. The slow process we expect to take us from the sort of iron region, just trapping up this staircase here, sticking very close to the line of stability there, just occasionally getting into the slightly radioactive things, and then beta decaying, and beta decay moves this way on this diagram. And so you get so far, but it couldn't explain essentially many of these elements here. As soon as you get gaps, and you won't see this too well on the screen, But as soon as you get gaps here, it becomes harder to explain through the S process. And instead, well, let's have a look what happens with this R process if we can set it going. We imagine now if there's a rapid process that fires neutrons in very quickly, it can pull all the nuclei over to this side of the diagram so that they become extremely unstable, but they keep on having nuclei fired at them and work, as we'll see, their way up this figure. Oh yes, there we're going. So there we're going, the temperature is very high, the time is very short, we're pushing these nuclei up here, they get stuck, hung up at these magic numbers, and then once the neutrons are turned off, they decay essentially diagonally on this plot, and so you end up creating peaks which are offset from where the magic numbers would lead you to believe they should be, because they decayed from a line that was offset in the first place. So that was clear in the 1950s. It was clear that there must be somewhere in the universe, if we want to create many of these heavy elements, including elements as well like uranium, for example, which wouldn't be created in the S process, you needed to have somewhere in the universe where this rapid injection of neutrons was taking place. And for many years, it was just kind of assumed that that must be happening in supernovae. You know, those were explosive environments. You thought probably in some kinds of supernovae, at least, this must occur. This may still be true, but for a long time, it was also the case that the theorists that worked on supernovae found it rather hard to find such conditions. And so an alternative hypothesis was made, namely that perhaps merging neutron stars were an alternative place where you could get a lot of neutrons. Why not? So this is what a neutron star looks like. This again, obviously, artist's impression, very intense magnetic field in many cases, and so that's illustrated there. What kind of size are we talking about? Oh, you know, about the size of an East Midlands city. We don't really have neutron stars floating around there, but that's what it would look like if we did. They're remnants as well of supernovae. They're the sort of nugget that is left of the core of the star once the rest of the star has exploded. And the density is the thing, of course, I emphasized at the outset was made them very remarkable. But essentially, the density is comparable to the densities of atomic nuclei. And of course, that means that they're very substantially made up of neutrons. That kind of density, you've got to be thinking about sort of, you know, 1,000 trillion times the density of normal matter. And what happens if you merge two neutron stars together then, like that? This is a simulation, but what you can see, actually what you don't see, is that the final merger contains most of the mass of the two neutron stars, and maybe it forms a black hole, or maybe it forms just a heavier neutron star. But you can also see a fair amount of material has been thrown out in that process. So this is just a simulation. It's quite an old simulation now, but it's one that is, I think, visually quite impactful. So I like to show this one. So we get that feeling that there could be material thrown out of neutron stars when they merge. That would be a location where you'd get a lot of neutrons. You could therefore start building up the R process elements in that kind of environment. Obviously, you don't know what's happening here in the middle, but that's kind of by the by, because that lot is not coming out. This stuff is being expelled, and so is of interest to us. Okay. In fact, it's particularly interesting because it was also realized that those R process elements, if they are created by the material thrown out of neutron star mergers, should also create a lot of energy, essentially by that radioactive decay of all those elements that we just saw. And so that leads you to predict that that material is not just thrown out of the mergers, but then it essentially explodes, and so produces something a bit like a supernova, but not quite as big and bright. And so, well, you might ask, what are you going to call it? If it's between a nova and a supernova, you might call it a pretty good nova, according to that cartoon. Or more commonly, although the nomenclature is not fully settled, people have different names for the same thing, but I'll refer to it as a kilonova. One reason for preferring that name is that it confuses journalists who think you've said kilonova and therefore get very excited that we might be talking about something threatening life on Earth. Okay, right. So now we're going to park that. We're now going to talk about gamma ray bursts, and in particular these short duration gamma ray bursts, again, that I introduced at the outset. Gamma rays, of course, are the most high energy forms of light, not very healthy. You don't want to get too many gamma rays going through you. Thankfully, they're stopped by the Earth's atmosphere, but that also meant if you were an astronomer interested in using them to study the universe, you needed to get above the atmosphere in order to look for them. And that wasn't done until the 1960s. It was done, amusingly enough, not for the purposes of astrophysics, but because the US wanted to monitor the compliance of the Soviet Union with the Nuclear Test Ban Treaty, which has said thou shalt not explode nuclear bombs in space. And so in order to ensure that the Russians didn't do that, the US launched this series of satellites through the 1960s, which were able to detect flashes of gamma rays that could have come from nuclear tests in space. And sure enough, they detected flashes of gamma rays, but realized rather quickly that they were not from nuclear bombs. Instead, they seemed to be coming from beyond the solar system. And that was about all that was realized. And essentially, it's just like a Geiger counter. You're detecting clicks with these things. And so this is a little sort of time histogram of the clicks that they got on the very first example that was ever detected. What could give rise to the gamma ray burst? Well, for several decades, we continued to acquire data on gamma ray bursts, and almost the only thing that was learned was that they seem to come in two sorts. So I'm not going to spend time explaining this figure fully, but what you can see is that there do seem to be sort of two clusters of points. There's a cluster of points here where that flash of gamma rays is some tens of seconds long. And then there's another cluster of points where the flash of gamma rays is more like about a second in duration. And they do seem to be separated on this plot. And so these guys here in the pink circle are my short duration gamma ray bursts. These ones are the long duration gamma ray bursts. And those are tremendously interesting as well, but that's another story. We're going to be concentrating on the short duration class. What we have learned subsequently from observations of GRBs, actually both the long and the short, is that they don't just come from beyond our solar system, they come from beyond our galaxy. Indeed, they typically come from galaxies far away across the universe. We understand that the radiation they produce is likely due to them emitting jets of material that's illustrated in this little cartoon here, moving at something very, very close to the speed of light. So 99.999% of the speed of light. If you can eject a jet of material like that, and if you happen to be looking down the jet, then you'll see something that has all the characteristics of one of these gamma ray bursts. The fact that they're occurring in these distant galaxies, but still create flashes from the point of view of the gamma ray satellites, which seem to sort of light up the sky in some sense, from a gamma ray point of view, tells us that the total amount of power that we're seeing can be up to something like this times the power output of the sun. Only briefly, but nonetheless, that's an impressive number, and very intriguing to know where that kind of power might be generated. So come back to the neutron star. The neutron star and black holes as well, but neutron stars, this talk are what we're most interested in. They can release energy essentially because of the potential energy that's lost when you drop stuff into the neutron star. So this is my little neutron star. You can barely see it on that screen, but that's a little black ball. I'm imagining now that I'm going to drop a pea onto this neutron star from some, fairly significant height. The neutron star, we said, is only, sort of 10, 20 kilometers in diameter here. we're going to drop our P from some height onto that neutron star and see how much energy is released. And schematically, I'm telling you that it's roughly a sort of atomic bomb's worth of energy. You can do this calculation yourselves. I'd encourage you to do so. Just using basic Newtonian equations, you can quickly realize that's the potential energy that a P landing on a neutron star would give out. And so you only have to tap some of that. You have to turn some of that into outward going radiation or a jet, and you've potentially got quite a lot of energy to play with. You can get even more energy, of course, if you drop another neutron star onto your first neutron star instead of a P. And so another one of these movies, this one's just a sort of cartoon, but this one's designed to show you something particular, which is the production of these jets. So essentially that was the picture. We had this picture that not only when you merge two neutron stars did you create gravitational waves, we saw that kind of right at the beginning. Not only do you potentially create these R-process elements, which we saw a moment ago, but if the merging of two neutron stars also creates a jet, and it's still an open research topic, exactly how such a jet might be produced, but if it can, and we don't have many other possibilities, so this is the leading contender, then that could explain these short duration gamma ray bursts. Okay, so that's how we're sort of linking together all these things. The question is now, that's the sort of, the theory or the idea behind it. What about observations? Can we actually provide links between all of these different phenomena? And the first occasion on which we thought one of those links was back in 2013, and gamma ray bursts are not discovered all that often, and when they are, they're given the date as the number of the burst. So 2013, June the 3rd, second burst of the day, that's why it has a B. Oh, pardon me, go back. Right. So this was a short duration gamma ray burst. We observed it rather quickly with the Hubble Space Telescope, well, with various telescopes around the world. We realized it was reasonably close by to the Milky Way, which means it was about 2 billion light years away or so, so not very close, but close enough that we thought it was worth training the Hubble Space Telescope on it. What did we see? Well, first thing we see is we see the host galaxy, the galaxy in which this binary merger, we're supposing this short duration GRB took place. And what we saw was that in exactly the position where the GRB had been, a week after the burst went off, there's a little red blob. You can barely notice that little red blob. It hardly looks any different from the rest of the galaxy. But by taking another picture with the Hubble several weeks later, you see, hopefully at the end of the arrow, there's a bit of missing red light that was here and is not there. Well, that was our evidence, may seem rather scant, but that was our evidence, our argument that we'd seen the light of the kilonova that we supposed also accompanied this merger. So let me just explain that then. The idea is that the neutron stars merge very quickly, as you saw in a fraction of a second, that final inspiral merger. The jet comes launching out and creates the short duration gamma ray burst very quickly on the time scale of seconds. The kilonova, which we're saying is produced by the material thrown off in the merger, is a much slower kind of explosion. We predicted that that would only come and reach sort of peak luminosity many days after the merger event. And so seeing this light when the gamma ray burst itself had faded away was fairly suggestive, we thought, that we'd found a kilonova. The fact that it's red light also turns out to be important, and we'll come back to that in a moment. But there had been a prediction that the light essentially from the kilonova should become red because those heavy elements themselves act as a kind of smoke screen. They block the optical light rather effectively and release the light instead more in the infrared part of the spectrum, which is actually where these pictures were taken. Okay, let's press on. Let's press on another 4 years or so when we had a big breakthrough. I don't know if you heard that. I turned the I turned the sound up on the laptop in the hope people would hear it. If you did hear it, what you heard was the gravitational wave signal turn into a sound form, getting higher and higher pitched as the two neutron stars get closer and closer together, just in the last few seconds of their lives. So this detection was made on the 17th of August 2017. It was the first time that the gravitational wave detectors had seen something that they said looked like neutron stars rather than black holes. So we immediately sat up and took notice. What made us take extra notice was that this satellite, the Fermi satellite, also detected a flash of gamma rays just less than 2 seconds after the gravitational waves, coming from roughly the same part of the sky, as we'll see in a moment. And so suddenly this looked as if this was joining two other bits of the puzzle together. Gravitational waves from binary neutron star merger that also produce gamma rays, just as we would expect if short GRBs were produced in the same way. So that led us then to a challenge. It led us to a challenge which those of us involved in this, we were wrestling with for many hours on that day, the 17th of August. The challenge was this, that the gamma rays from that particular satellite, it doesn't have very good localization capability. It could only kind of tell us the thing happened over there. And so if you're looking for other forms of light, which we were, like kilonova light, you had a large amount of space to look in, not very practical. Thankfully, the gravitational wave detectors, by virtue of the fact that we now had 2 in the US and 1 in Europe, were able to give a much better localization, and that's illustrated by that green ellipse there. And what you can see is that within the green ellipse, the little black dots that you see in that green ellipse, those of you with good eyesight, those are galaxies that are near enough by that they could have produced such a strong gravitational wave signal. So I didn't tell you that so far, but it was a relatively strong gravitational wave signal. It meant that this event had to be within about 130 million light years or so, so relatively nearby to us. Not so many galaxies then within that volume of space. And that gave us a chance, we thought, of identifying them. And we trained a whole lot of telescopes actually around the world, mainly in South America, mainly in Chile, also the Hubble Space Telescope again, on this set of galaxies. And indeed, to cut a long story short, we found one in which there was an exotic new explosion taking place just as we looked at it. And you can see this is my attempt to make a movie of that. Again, you've got a galaxy. This is the galaxy in which the explosion is taking place. You may have already spotted that there was something happening up here. It's a time-lapse image. I'm rerunning the movie a couple of times. The time-lapse movie, the explosion that we were looking for is that thing up there. So this is just one of those galaxies within that big ellipse. All of the rest of these things are just stars. That's the explosion that we think is the kilonova. You'll notice that it starts very blue and then turns red. That, in a sense, was a confirmation of what was expected. I mean, just how blue it was quite surprising, but it had been predicted that you could start off with an early blue phase, and then gradually the sort of smoke screen effect would take over, and you would turn red, and so it was. So the whole movie lasts over the course of about 3 weeks. But yeah, once we found it, of course, then it was the subject of enormous scrutiny, and finally seemed to tie together then all of these stories. It looked as if we had what was undoubtedly a neutron star merger, because the gravitational waves tell you that it couldn't be produced by anything else. It was accompanied by a flash of gamma rays, which gives pretty good confidence that it was also a short duration gamma ray burst. And we observed this explosion, this slower explosion, which had all the characteristics that we wanted to see from a kilonova. So what are my conclusions then? How am I doing for time? Oh, not too bad, good. The conclusions then are that, first of all, Wikipedia had to change their web page. So for a long time, if you'd have looked up nuclear synthesis on Wikipedia, you'd have seen a periodic table like this. You would have seen the stuff that's of interest for us is all the purple stuff here. And what it would have said was that that purple stuff, all of those elements, or at least many of the isotopes of these elements, and the relative abundances of the different isotopes, these are all the R process elements and R process isotopes. And it would have said they're created in supernovae. And this had irritated me for some time, I'm sure other people as well, because we knew that this was a controversial suggestion. We knew that the supernova theorists were not finding much evidence of creation of these R process elements. We knew that merging neutron stars was an alternative. And within probably days anyway of the announcement of the discovery of that 1708-17 gravitational wave related kilonova, everything changed. This plot was changed so that merging neutron stars became the recognized source of these R process elements. Now I have to tell you, in a sense, Wikipedia may yet have to change again, because the truth of the matter is this is still a very much an ongoing area of research. What we really want to know, whilst we're confident now that merging neutron stars almost certainly do provide some of the R process elements in the universe, we are not fully confident that they can explain all of the R process elements in the amounts that we see. And so it's still speculated that there could be some supernova contributions, different kinds of rather exotic supernovae that could give rise to some R process elements. And in particular, those could be most useful for explaining the fact that we do see some R process elements in what seem to be very old stars, stars that must have been formed pretty early on in the lifetime of the universe, rather before you'd expect merging neutron stars to be spraying their elements out into space, because that takes some time to form neutron stars and then have them merge together and then explode. All takes time. It's much quicker to create some supernovae because massive stars have very short lifetimes. And so there's still a good deal of debate and ongoing research going on, but it's nice to at least see merging neutron stars up here as being at least the most well-supported contender for their the production. And you can really see, I think, from this diagram how important it was, how big a mystery. So I told you it was a mystery. Where do the heavy chemical elements come from right at the outset? And you might have thought I was over-egging that, but you get this appreciation of just the amount of purple on here. We really had, up until just 5 years ago, a very sketchy idea of where, in terms of the cosmic sense, many of these elements and isotopes originated. What else can we say? Well, again, just to do the Carl Sagan thing, if he can say that we're all made of stardust, from now on, we can also consider that we're also, to a certain extent, neutron stardust, which is a pretty profound thing, really. This notion that, you know, whatever you might be carrying around, for example, you know, on your person that's made of gold or one of these other heavy elements, originated at some point many billions of years ago in probably a neutron star merger within the Milky Way, finally got incorporated in the solar system, in the Earth, and then was eventually dug up, and finally you bought it in some shop in the Grand Arcade at the end of that whole process. Okay, thank you. I'm done.
Thank you, Professor Nial Tanvir, for the very interesting talk. We'll now move on to the Q&A segment. So if anyone has a question, please raise your hands and wait to be called. We can also take a few questions from our online audience. So please put your questions in the chat if you have any. Right, right over at the back, Rachel.
Hi, thanks for the talk. That's really interesting. I noticed that in the two examples of kilonovae that you showed the observations, they're both quite situated on the edge of their galaxies. Is that a genuine thing that we expect? Is it coincident with a certain example, or?
So, yeah, okay. Interesting question, actually. And it's not unexpected. And the reason is that neutron stars, and particularly binaries that have had time to undergo that inspiral, that can take hundreds of millions or billions of years. So you do not expect typically to find them happening in, let's say, intensive regions of star formation where lots of new stars are being born and dying on a timescale of millions of years. You might find a binary happening there, but it would be unlikely. There's actually a more interesting thing, which is that we know that each time, in order to create both of those neutron stars, you have to have two supernovae. You have a binary star, two massive stars, each of them go supernovae. When that happens, very frequently, the neutron star gets what we call a kick. It gets a certain amount of velocity, sometimes quite substantial velocity added to it. So these things explode. The first one explodes, and then the binary is going off, and then the second one explodes, and it's actually by now got some quite high velocity. If you then allow it some billions of years before it merges, it can take the system actually way outside of its galaxy. And we have examples of short duration gamma ray bursts that look exactly like that. We didn't see one there, where this is the galaxy, and you know, the short duration gamma ray burst is happening over here. So funnily enough, it so happens that those two I showed you, although they might have looked like they were on the outskirts, actually those are amongst the ones that are most sort of on the inskirts of their galaxies, as it happens. Partly, I guess, certainly in the first case I showed you, unless you actually have one that's happening kind of within its galaxy, you're not 100% sure that that is the host galaxy. So I'm drawing you a picture of one happening over here and the galaxy being there. Of course, you're never quite secure then with that association, whereas if it's happening here, you can be confident. And that's quite important because measuring the distances to these things turns out to be very hard if you're only looking at the gamma ray burst. Much easier to measure the distance to the galaxy that you think is the host. So typically that's how we do it.
Over there.
So you said that field is very rapid and around that. Why is that the case?
Oh, right. Well, I think it's just a frequency thing. So they could happen in principle, but they are rare events. So in any given galaxy, you know, you might have to wait some, you know, hundreds of thousands or millions of years for one to occur. It's also you know, it's an important health and safety thing because if one does happen, you know, within the Milky Way, within, you know, let's say sort of 10% of the size of the Milky Way and is pointing at us, it's not very good news. So to some extent, we can be pretty thankful that they're rather rare, and so, you know, you're very unlikely it's not the most likely way that the Earth is going to end catastrophically, shall I put it that way? There are other ways that the Earth could end in a catastrophic way that are of a higher likelihood. Again, I'm drifting slightly off topic here, but there is also what I didn't talk about with the long duration gamma ray bursts. Those are even more powerful, actually, and those we think occur predominantly, or certainly more often, amongst stars which are relatively pristine. In other words, ones that don't have a lot of these heavier elements within them. In other words, they typically happen more often in the earlier universe than they do now. So in a galaxy like the Milky Way, we think that we're kind of protected from those long duration gamma ray bursts because we already have quite an enriched gas, and so new stars that are forming out of gas that has already been enriched, and that turns out, for complicated reasons, not to lead to as many gamma ray bursts. And so, for all those reasons, we don't expect to find any in our immediate neighborhood.
Do we have more questions?
I could show you another movie if you're wanting to think about it. So there was a movie made. Oh no! Wait a minute. I had some slightly. I'd forgotten. I had the last few slides. Apologies. Let me spin quickly through the last few slides. I'd forgotten I'd got this. So this was, you know, a natural question you might have asked me. No one has so far. Is what's happened in the last 5 years then since you discovered the last one? And one thing that's happened is that 3 guys won the Nobel Prize for the gravitational wave discoveries. What you might have then said was, well, do we now know the full story? We'd like to know more, basically, but we haven't found any more kilonovae. So there was a long science run which took place in 2019 into 2020, where there were 2 or 3 other systems found which looked like they involved neutron stars. And the problem for us as people who wanted to go and look in other forms of light for those kilonovae was that these were much further away. So these were already much more challenging. There were also much bigger areas of sky for one reason or another. And so we tried, but we never found another example during that year. The next run has been sort of delayed by COVID and is expected to happen at the end of this year. So we're going to try again. We're hoping, of course, that we will find more kilonovae, but I suppose the final thing is, and this guy, Ron Drever, I highlight him because he was one of the people who was slated to be one of the Nobel Prize recipients, but he died just before the decision was made. And so I guess he might tell you it's a hard game. He worked for most of his career on looking for gravitational waves. I'm warning you that it may also be slow progress in pushing on with this field for that reason, that these kilonovae, we were very lucky in 2017. We found a really nearby example that had all of the things that we wanted associated with it. Our expectation going forward for the next 5, 10, 15 years is that it's going to be quite hard work to find other examples and to sort of improve our knowledge. So I think we will, but it's not going to come like a great sudden rush of new information. And finally, yeah, there is this movie that NASA made, I think, or someone made anyway. Again, it's a schematic movie showing all of the components that we think happen in the 17th It's selling material by a variety of processes. They're producing green kilonovae and red kilonovae. The final thing out there is showing something that I didn't talk about, but we detected, if you like, the sort of the jets as they had plowed on a long way. In this instance, we weren't looking down the jet. So in fact, we didn't really see the jet initially, but eventually as the jet slows down, we start to be able to see it more from the side. And so we carried on observing actually now for several years, the light from that jet as it sort of hits the ambient, sparse, but still there, medium around the merging neutron stars. We were able to see the light from the jets hitting into that medium. There you go. So that's my second ending of the talk.
Right, with a question from Michael, will the James Webb Telescope help to find these, I guess, neutron star mergers?
Okay, good question. So James Webb Space Telescope just launched last Christmas Day, and immensely powerful. It's going to change many areas of astronomy, I'm sure, in its kind of 10-year hoped lifetime. What it really brings to the table is the infrared. So you've already seen that the infrared is important for these kinds of objects, particularly the kilonovae. The James Webb Space Telescope is particularly designed to look in the infrared for a variety of things: distant galaxies, planets around other stars, many things you can observe in the infrared. It's much more interesting to observe them in the infrared than it is in the optical. So that's exactly what the Webb is meant to do. Gives us access to a whole lot of infrared wavelengths that we can't observe, for instance, with the Hubble. What it won't do is allow us to find these things really very easily. So the James Webb Space Telescope has a very small field of view. So it's not going to go around the sky hunting for them. But if we can use other telescopes to localize them down and say, essentially, to the Webb, this is where you need to look, this is the galaxy in which this explosion has occurred, it will then give us an unprecedented view. And indeed, time has already been allocated on the James Webb Space Telescope for this kind of event. If it happens, then it will override the other observations that it might be doing and will turn on a time scale of a few days. It doesn't happen super quickly, but it will turn slowly towards that target. And because those explosions, as I explained, take place over a few days, actually the timing is not too bad. It means that one can get there and still make some very interesting observations.
Right, I'll ask the question as well. So from the plot with the blue and orange dots, you will see black holes merging to black holes and neutron stars merging to black holes. Do you get neutron star and black hole mergers?
Oh yes, there's another good question. and absolutely, you know, kind of an intriguing one, because of course, every now and again, you will indeed get a system that's a neutron star and a black hole. So why wouldn't they merge? You will learn by now that they will. Indeed, there was at least one pretty good case from the last science run where it looked as if that is exactly what had happened. So if you use the gravitational waves to tell you what was it that merged, the answer is it was a neutron star and a black hole. We again expect some neutron star material to be lost in that process, so it could easily produce a kilonova-like explosion. We do expect it to be different though, and so the issues are a bit complex. Basically, so if you imagine we're smashing two neutron stars together, you saw in that movie that those sort of tidal tails would throw material out. You'd also get material thrown out when they smash together. You also, as it turns out, get material ejected in what we call a wind, where the material basically gets hot as it's falling into the neutron star or black hole, and it blows away a certain amount of it. And so all of those different processes are blowing material off one way or another. Now, in the case of a neutron star going into a black hole, of course, if the black hole's too big, actually the neutron star just drops in before it has a chance to lose any material. And that was the case for the one that we've detected so far. So we never really expected to see anything, and we didn't see anything, apart from the gravitational waves. If it's a slightly smaller black hole, then indeed you get a certain amount of material thrown off, but mainly through those tidal processes. And so that we think is going to produce a different characteristic of kilonova. We still don't know how much material is thrown off. This is a very observationally driven science in some ways. The theory, the amount of physics in there is tremendously interesting, because you've got gravitational physics, you've got nuclear physics, atomic physics, all of these different complicated areas that have to be brought to bear. And the problem is that, of course, is that there are lots of uncertainties, lots of things we don't understand about how nuclear matter, for example, behaves in detail. Even the atomic physics, which is just electrons moving around within the atoms, which you might think was very well understood, turns out not to be so well understood when you're talking about these big, heavy atoms that have a lot of electrons and many, many, many different transitions possible. So there's a lot of complicated theory, tremendously interesting, but hard. And so really, from an observational point of view, that, you know, there are many questions that one can answer from observations, which are really tough theoretically. And actually it goes beyond, I haven't had time to talk about it, but it goes beyond just understanding production of elements and that sort of thing, which is a big question. But you can also do with these observations tests, for instance, like, does gravity travel at the same speed as light? We've always assumed that's the case. Eddington thought it was the case when he wrote his paper in 1922, but you know, it's something that you can go out and test with these observations. And the fact that the gamma rays arrive actually about a second and a half after the gravitational waves is pretty good confidence. They're certainly coming at very, very close to the same speed, even if there's some wiggle room there for a very, very slight difference, but most likely indeed they are coming at essentially the same speed. But these are kind of very fundamental physics tests that you can do through these sorts of systems.
Do we have any more questions from the audience here? All right, I guess then that will be it for tonight. Thank you once again to Professor Nial Tanvir for the wonderful talk, and thank you everyone for coming tonight. Just a short reminder, if you've read the emails, that the QA committee is open for nominations, and we'll be having our AGM in 2 weeks. So if you'd like to run for the committee, feel free to have a chat with us or email me if you want to express your interest. And otherwise, that's all, and hope to see you guys next week. Thank you.